question regarding the lecture yesterday? So what I'd like to do today is spend the first 5 minutes or so to review what we learned yesterday, and then discuss more about possible solutions. So yesterday we saw one solution, which is a half wavelet, very simple solution. So here we have introduced additional solution. Okay, and given those solutions, how to find, given all the choices of half band filter, how to factorize or how to choose the appropriate choice of H0 and F0. Okay? So what yesterday we discussed the properties and definition of downsampling, of upsampling, of decimation, so the cascade of a filter, and downsample for decimation. Now, who remember why do we need a filter before downsampling? Because of aliasing, right? So we need before downsampling. We want small or no aliasing, then we have to have a filter, which is a band pass, a low pass filter, band limited to pi/2, right? In this case. So here is decimation, here is interpolation. So who remember why do we need a filter after upsampling? So to fill in the zero value. Right, so that depends on what do we use. If we use a low pass filter, then the resulting interpolated signal will be a smooth copy of what we have. If we use a high pass filter, then you have a highly varying signal, and so on. Okay? So for the case of 2-channel, we have two choices of filters: a low pass or high pass filter. Okay? And one other thing you want to remember is the first branch basically capture low frequency signal, low frequency component, and the second branch capture high frequency component. If we have application where you don't need to use the second branch, you don't have to. So there's no signal there, for example. Okay, so this way, as you see later on, we'll be able to decompose or divide the signal into different bands. Okay? So one question we ask is that, okay, we can decompose, but can we reconstruct? Right? So the question of how to reconstruct and what kind of error do we have? We know that if this is an ideal filter, then there's no aliasing, no distortion whatsoever. Right? And if we have a practical filter, then we have aliasing here. Okay? So we have aliasing, we have imaging, distortion, and so on and so forth. How do we find these four filters such that the output is a copy of the input, and we allow some delay? Okay? So that's the statement is that how do we find the possible choices of filters such that the output is a copy of the input. Now, there are many ways to solve this, and we see that on today. We look at polyphase representation, where we have another more efficient way to figure out the PR condition. So this is called PR, for perfect reconstruction. But for right now, what we have done yesterday is we take x band with d prime of x of z. We carry it through the whole system, right? We measure what this is, which is the product H0 and X. Then we go through the cascade of downsampling and upsampling. And we see that this signal is basically the combination of that one and then with a shifted by pi. Okay? And so on. So after we know of this, we find a condition for FIR solution. So here's a summary. Basically what you have to do is you have to find a half band filter, P0 of z. Okay? And after we find a half band filter P0 of z, we factorize P0 into F and H. Okay? And when you do that, you're done. Because the other two filters is basically related to H0 and F0, right? So if you look at this, What is f1 of n equal to? I'm sorry, f0. So this is how we relate it in the frequency domain or z domain. What is it in the time domain? Minus 1 to the n h1 of n, right? So we know that if I know h1, if I know f0, I can find h1 and so on. So f0, h1 are related this way. And then this one here, f1 of n is minus 1 to the n h0 of n. So f1 and h0 this way. That's how they relate it. Okay? Alright. And we also show that L is an odd integer, right? Okay? So yesterday we have one example of what would be P0, a half-band filter. And the easiest one that we have yesterday is P0 is 1/2 1 plus z inverse squared, right? So in the time domain, this P0 will be basically at 1. So this is 1 plus 2 z inverse plus z inverse z minus 2. So you have at 1 is 1, and then 1/2 at 0, and 1/2 at 2, and 0 elsewhere. That's how the impulse response P0 of n looks like. Is this a half-band filter? Yes. Because it is 1, right, on an odd integer. We need it here. So here's L. If L is 1 in this case, and then 2 points away from it. So in this case, minus 1 and 3 is 0 and so on. So this is one of the very simple, right, half-band filters. So suppose this is your choice of your half-band filters. Then what could be the factorization? Well, to do that, we have to find, again, this is FAR solution. So you have to find all the 0 of P0. Then allocate the 0 to either F0 or H0. Okay, so there are many ways of doing this. So let's go to them. F0, Z, F0, and H0. Okay, so here is the Z-plane plot, the pole 0 plot for P0. Here is pole 0 plot for F0 and H0. So what are the 0 for P0 of Z? Minus 1. So that to find 0, remember that we need to find where this function goes to 0, right? So as Z equals minus 1, so this is 1 is minus 1. So we have 2 0, it's a double 0, at minus 1. That's it. Okay? So we have 3 choices, right? But the normal, the fair way of allocate is 0. It's 1 for each. Okay? The other choices are not very useful. So here I can allocate 1 to F0, 1 to H0. So in the Z domain, P0 of Z is 1/2 1 plus Z inverse square equals 0. Right? The product of these two. So each of them look exactly the same, right? This one was 0, 2, 1 plus Z inverse. That's F0. Another one is 1 over 0.